Everyone, welcome to our Vegas tutorial. In today's class we are going to study about the cells in a series. For this we are going to consider the two cells here. One is having the EMF E1, the cell it is having EMF E1 and the internal resistance R1. This is having the EMF E2 and a resistance R2, and this is the equivalent EMF, the cell which is having the equivalent EMF R epsilon EQ and E EQ and R EQ. Okay, we have to consider first the potential difference between A and B, that is the potential difference between A and B. VAB is equal to, it is given as the potential difference between A and B, VAB is equal to E1 minus IR1. Similarly, potential difference between B and C, the point B and C, it is given as VBC is equal to E2 minus IR2. Okay, therefore the total potential difference between the point A and C, it is given by VAC is equal to E1 minus IR1 plus E2 minus IR2. Okay, now I take this to the other left hand side and this to the right hand side, or you just rearrange the terms. You'll get E1 plus E2 minus IR1 minus IR2. This can be written as E1 plus E2 minus I is common, take it outside, then remaining is R1 plus R2. We can replace this some of the individual EMFs by the equivalent EMF, that is E equivalent minus I into, same way the internal resistance can be replaced by the equivalent internal resistance, that is IREQ. So this is the expression for potential difference, that is VAC, between the point VAC. Here the value of EQ is nothing but E1 plus E2. Suppose there are n number of cells having the EMFs E1, E2, E3 and so on up to En, then it becomes E1 plus E2 plus E3 and so on up to En. Same way resistance, equivalent resistance becomes R1 plus R2 plus R3 and so on up to Rn. Okay, Rn, this will be the expression for equivalent EMF and equivalent resistance, internal resistance for the cells when they are connected in the series combination. This will be asked for 3 marks in your final examination. Okay. Well, in today's class we are going to study about the Wheatstone Bridge. This is in the next part of the syllabus of the current electricity, Wheatstone Bridge. Okay, on what principle does this Wheatstone Bridge work is the principle of Kirchhoff's rule. In your previous video I have already studied about the Kirchhoff's rule, the first rule and the second rule, that is the junction rule and the loop rule. So this Wheatstone Bridge, it works on the principle of Kirchhoff's rule, and it is used to find the unknown resistance. Here R4 we are taking it as the unknown resistance, and it is also used to compare the resistance values. Okay, so what is the condition, balancing condition for the bridge is the current through this galvanometer has to be 0. That is the condition, balancing condition is Ig must always be equal to 0. Okay, coming to the construction of this Wheatstone Bridge, it consists of the 4 resistors here, R1, R2, R3 and R4. Okay, these are placed across one part of the diagonally opposite points, that is A and C. The source is connected here, it is called as battery, between the arms B and D, between the arms B and D, and the galvanometer is connected G here, it is between the B and D arms. This arm is called as galvanometer arm. So to obtain the balancing condition for the Wheatstone network, we are going to derive an expression here. By assuming Ig is equal to 0, we are going to apply the Kirchhoff's rule between D and B. D and B here, that is I1 is equal to I3 and I2 is equal to I4. Okay. Now we are going to apply the Kirchhoff's loop rule, that is the closed loop for A, D, B, A and C, B, D, C. A, D, B, A and C, D, B, C. We are going to apply the Kirchhoff's loop rule here, and we get I1 R1 plus 0. Here I1 R1 plus 0 plus I2 R2 is equal to 0. 0 here because the current through the galvanometer is 0. I1 R1 0 plus I2 R2 is equal to 0. Take this as equation number 1. Same way for the second loop. For the second loop, we can write it as I2 R4 plus 0 minus I1 R3 is equal to 0. Take this as equation number 2. Right? From equation number 1 and 2. From equation 1 and equation 2, we can write it as I1 divided by R1 is equal to, I1 divided by I2. I1 divided by I2 is equal to R2 divided by R1. Take this as equation number 3. Okay. Similarly, from equation number 2, this we got from equation number 1, and from equation number 2, we are having I1 divided by I2 is equal to R4 divided by R3. Take this as equation number 4. Now compare equation 3 and equation 4. We can write, comparing these two equations, we can write the left hand side is equal. We can write R2 divided by R1 is equal to R4 divided by R3. Okay. So this is the required equation here. This is the equation for balanced condition of Wheatstone network. When Ig is equal to 0, this is the required equation for Wheatstone network. Suppose R2, R1, R3, these three resistances are known, then we can calculate the value of R4. R4 as R3 into R2 divided by R1. Because we have already considered here R4 as the unknown resistance, it can be calculated using this formula here. So in this equation, you have to draw the diagram, then you have to write the principle, working, construction, and derive this expression for the balancing condition of the Wheatstone network, taking Ig is equal to 0. This whole derivation along with the neat labeled diagram carries 5 marks. Okay.